Today we're going to be looking at eigenvalues and eigenvectors. So we're going to be using this question as an example. Okay, so the first part of the question is, you have in 2022, an investment firm undertook an analysis to examine the diversification effect across three primary investment categories: equities, commodities, and real estate. The covariant matrix Q that represents the quarterly return correlations over the last several years is provided below. So you have a 3x3 matrix there representing the covariant matrix of the quarterly returns for the last few years. So part I of the question is calculate the eigenvalues of that covariant matrix Q and determine the percentage of variance explained by each principal component based on these eigenvalues. Right, you have to show all your calculations. That's what 10 marks. The second part of the question is find the eigenvectors for the covariant matrix Q based on the eigenvalues calculated in part I and interpret what each principal component suggests about investment behaviors. And then the next part of the question is provide detailed steps for finding these eigenvectors. The third part is determine how many principal components are required to explain at least 70% of the total variance. Provide the calculations to support, your decision. That's what 2.5 marks. Again, you have to look at the weighting of the marks to see how long you should spend on each part or how important each part is. The fourth part of the question is construct a screen plot based on the PCA analysis. This plot should illustrate the eigenvalues and help visualize how components contribute, which components contribute most to the variance. Again, that's with 5 marks. So it's a quite solid question, quite dense, but we look at it part by part. So the first part is asking you to calculate the eigenvalues and then find the percentage of each, the percentage each principal component contributes to the variance. So I have the formula there for finding the determinant because we know that to get the eigenvalues, we need to solve for this. We need to solve the determinant of this, where you have Q is the original matrix and you have lambda there times the identity matrix, which is a 3x3 identity matrix, because 0, we have to solve for that. So that's how you get the eigenvalues of a 3x3. And to get the determinant, which is det here, det, we use this formula here, which is saying that determinant of that, to remind you, it's A, and then so what you do is you look at A and you multiply it by, you cover the column and the row that it's in, and then you multiply EI minus FH, and then you go minus B, you cover the column it is in and the row it is in. So B times DI minus FG. And then you do plus. You see that there's a difference there. There's a minus here, there's a plus here. That's just how the formula works. So you have the plus C multiplied by, so you close the column and the row. So multiplied by DH minus EG. So that's how you get the determinant. So anyway, so first we have to find out what's in the brackets there. So we have to get Q, take away the identity matrix multiplied by this lambda there, which is the eigenvalues we'll be looking for. So pretty much what that means is because it's an identity matrix, it's only as 1 across the leading diagonal. So everything else is zeros. So that means the only thing affected in the original matrix Q is the diagonal, the leading diagonal, which means that it's always going to be this case. You're always going to have the same matrix, but in the diagonal, we're going to have minus lambda for every value. So that will be 6 minus lambda. It was only 6 before, 5 and 7 before, but now it's 6 minus lambda, 5 minus lambda, 7 minus lambda equals 0, and we have to solve for that. So again, remember, we have to get the determinant of that and solve for that. So to get the determinant, we're going to use this. Okay, so we're going to do 6 minus lambda times this 2 multiplied by this 2. Sorry, this 2 multiply each other minus this 2 multiply each other. And then minus B, which would be 2 in this case. So 2 multiplied by this diagonals here. 2, 0 multiplied by 2 and 2 times 7 minus lambda, etc. So you just use this formula. You end up with this. And so you expand everything. So if you expand everything, multiply everything out, you end up with a cubic equation. So in this cubic equation, we have to solve it. Because it's cubic, we have to factorize it. So to do that, one of the methods is to use try and error. So try and error, the way it works is you try values from 0 and we keep incrementing by 1. So try 0, 1, 2, 3, da, da, da. Because you're doing PCA and it's on pen and paper, we expect whole number values. So it's not always the case if you're using a computer, the values don't have to be whole number values. But because it's pen and paper, we need to use whole number values so that we can be able to do it on pen and paper. So it's always going to be positive whole number values that we're going to be trying to put in. So we should start from 0, we go to 1, 2, 3, and we keep increasing. So when we do that, we get the first vector or the first root So when you put that in, when we put in 0, it doesn't work, obviously, because there's this value here. When you put in 1, if you put that in, you don't get 0. You put in 2, it doesn't work. You put in 3, it does work. So when you put in 3, it does work. You know that 3 is a root. So that means if you turn it into a factor, so lambda equals 3 is a root. So the factor will be lambda minus 3. So that's the factor. So we know that a cubic equation is made of a linear factor and a quadratic factor. So we can use that to our advantage to find the quadratic factor. So there are two ways. You can either use log division. So when you have this, you can either divide it into this and get the quadratic equation and then get the factors from that. So that's one way, which we're not going to do in this case. Another way would be to use substitution, where we know that the other factor, when you have the linear one, the other one is a quadratic. So we know that when you multiply them, they should give us the original. So the quadratic one, we don't know the coefficients, which is what we're looking for. So A, B, C are the coefficients of the quadratic. We don't know them. So we put them there as A, B, C, and we're going to be hunting them down. So if you multiply that out, expand that, you end up with this. So now what we're going to do is we're going to just substitute or correlate this to this and just try to find out the coefficient. So for example, by just looking at everything that is cubed, this one and this one, we know that A is -1, and then looking at the things with the squares, so this and this versus this, so we know that B minus 3A is equal to 18, and then C, we can read it off, minus 3C is this. Okay, so when you solve for that, you end up with A is -1, B is 15, C is -54. So that means the quadratic for that would be minus lambda squared plus 15 lambda minus 54. So we're just subbing in A, B, C here. So when you have that, the next thing is, okay, we can take away the minus here. You can take it out so that we can factorize this. So if you take this minus out, you change the sign of everything. So this becomes lambda squared minus 15 plus 54. When you do that and you factorize the quadratic, you end up with lambda minus 9, lambda minus 6. So those are your factors. And then if you turn them into roots, you end up with lambda equals 3, lambda equals 9, and lambda equals 6. So those are your three roots, or your three eigenvalues, pretty much. And that's it. So that's the first part of that first part. The second part of the first part is determine the percentage of variance explained by each principal component. So principal components, how do they relate to this? Each eigenvalue is representing a principal component, and the biggest eigenvalue is the biggest principal component. So in this case, 9 is the biggest eigenvalue, which means it's representing the biggest principal component. 6 is the second biggest, it's representing PC2, or principal component number 2. And 3 is PC3, representing principal component number 3. So we need to know their contribution. So their contribution is really their ratio, how big they are. So 9 obviously is the biggest, but we need to see how big is it compared to the other ones, pretty much. So we know that the total variance then is the total of those eigenvalues. So 9 plus 3 plus 6, we get 18. So now if we wanted to find out the contribution of each, we just get the percentage. How much do they contribute to 18? So for PC1, which is represented by eigenvalue 9, we're going to have 9 over 18, which is 50%. For PC2, we're going to have 6 over 18, which is 33.33%. For PC3, we're going to have 3 over 18, which is 16.69%. So that's the contribution there. And if you see, it adds up to 100. So that's the first part done. The second part is asking for find eigenvectors of that matrix and interpret them. So to get the eigenvectors, we use the eigenvalues. So that means each eigenvalue has an eigenvector, right? So a vector is just a directional thing. In this case, it's a three-dimensional space, x, y, z. So a vector that is x, y, z component, or I, j, k component. But anyway, so we're going to try to find the eigenvector for this component. This is the principal component number 3, or the smallest one, which is given eigenvalue of 3. So when we pretty much what we're trying to solve is we have our original matrix, and then we have x, y, z, and then we're going to see, okay, if we're trying to solve this equation here pretty much every time when we're trying to find eigenvectors, we're trying to solve this equation. So what we're going to end up with is that this lambda changes depending on the eigenvalue we're looking at. In this case, we're looking for 3. So this is going to be 3. So if you want to solve this, we notice that the right-hand side is a 3 by 1 matrix. So that means we cannot move it around. So if you move it to the other side and try to take it away or something like that, we can't necessarily do that. And lambda is just a 1 by 1 matrix. So again, we cannot manipulate it. So, but we know that if you multiply by the identity matrix, if you multiply it by the identity matrix, technically doesn't change it. So for example, if you multiply lambda by the identity matrix, then that means, then it becomes a 3 by 3 matrix as well. So that means when that side becomes a 3 by 3, we can move it to the other side, which means that we can take it away from the original, and then we can say that, okay, so that is equal to so if you move it to the other side, so we can say that is equal to 0 because everything is now on the other side. So what that means then is that we're gonna have Q, our original matrix, minus an identity matrix that was multiplied by the eigenvalue, in this case 3. So remember, identity matrix only has values in the leading diagonal. So it only has 3's in the leading diagonal. So that means the only values affected in the original matrix are the leading diagonal, these ones. So that means we're going to have 6 minus 3, which we get 3. We're going to have 5 minus 3, which we get 2. We're going to have 7 minus 3, which we get 4. So those are the only ones affected. Everything else in the original remains the same. So you end up with this. And when you end up with this, you just have to create the equations then and let them equal to 0. So this is x, y, z, right? So 3x plus 2y minus 2z equals 0. 2x plus 2y equals 0. Minus 2x plus 4z equals 0. So you end up with those equations, you put them there, and you try to solve them. So to solve them, we are going to let x equals t. So if you let x equals t, and then you find out that if I substitute that into the second equation, if I put x equals t here, I end up with y is minus t. And if I do the same here, x equals t here, and I try to solve it, I end up with z equals 0.5t. So that means my eigenvector is gonna be 1 minus 1, 0.5, and you put the t outside, right? So t is multiplying everything. So 1 minus 1, 0.5, that's the eigenvector there. And then you have to put this statement here. It's important to put that in for all non-values of z. So for all non-zero values of t. So it means that obviously t could be anything, could be 5. So if I put 5 here, again, this will become 5 minus 5 and then 2.5. That's another eigenvector of this. Again, eigenvector, it doesn't really matter the actual numbers, it's the ratio that matters. So it's telling you how much weighting is on each component here. So it's just telling you how much weighting is on each component. So in this case, we're getting this kind of weighting. So for all non-zero values of t. And then you do the same for the second eigen value. So this time it's 6. So it means that we're going to be taking away 6 in the leading diagonal, pretty much. So the same thing, we're going to have q minus 6i, which is the identity matrix. So we're going to have 6 minus 6, you get 0. 5 minus 6, you get minus 1. 7 minus 6, you get 1. So you create the equation x, y, z. You end up with these equations. When you have those equations, the next thing is you solve them. So again, let x equals t. When you do that, when you substitute it in here, you get y is 2t. And when you substitute in here, you get z is 2t. Again, the eigenvector for that would be t outside 1, 2, 2. So 1, 2, 2. Again, if you put this statement, it's important to get full marks to put that statement at the end. And then the next part is getting the third eigenvector. So the third eigenvector, it's 9, which is really the, we're saying the third in terms of the order we did it, but that's the first principal component because that's the biggest eigenvalue. But anyway, so the third eigenvector, it's corresponds to the first principal component, which is 9. So we're going to have 9 taking away 9 in the leading diagonal. So it's going to be 6 minus 9. We end up with minus 3. 5 minus 9, minus 4. 7 minus 9, we end up with minus 2. Everything else remains the same. You create the equations. The equations will be 3x minus 3x plus 2y minus 2z, etc. So when you end up with the equations, you solve them again. X equals t. So when you have x equals t, you'd sub into the other equations. So if you sub it in here, you end up with y is 0.5t. If you sub it in here, you end up with z equals minus t, and then you just turn that into a vector. So that means t outside 1, 0.5 minus 1. And then for all non-values of z, for no non-zero values of t. So you get that. So that's the eigenvectors. Again, the last part of the question was interpret what each principal component suggests about the investment behaviors. So we kind of just have to interpret those dimensional vectors or those directional vectors, the eigenvectors. So we have to interpret them. So we know that we have 3 principal components. So PC1, 2, 3. So we put them there in this order because PC1 is the most important one or the one with the most variance. We put them there and we're like, okay, how does that relate to the investment behaviors? So those are the inputs that you have. So you have three inputs: equities, commodities, real estate. I'm just going to call them X, Y, Z because that's the order that I was given. So you have X, Y, Z, you have those, and you're saying, okay, so those inputs there, and how do they relate to the principal components? So we know that the eigenvectors really tell us the weighting of each direction, right? These are the directions or the dimensions, the weighting of each dimension on the principal component. So the first eigenvalue, so these are the eigenvalues, right? So the first principal component, which is really the eigenvalue number 9, which is the one we found last year. So it means that in the X, it is 1, in the Y, it is 0.5, in the Z, it is -1. This is the weighting ratio based. So that means there's a strong correlation with the between the PC1 and equities. So that means when I increase the equities, I increase PC1. Okay, there's a strong positive correlation. But this one, there's kind of half positive correlation, 0.5. Medium correlation between commodities and PC1. And then there's a negative correlation, negative and strong correlation, strong compared to the other, to this one, I guess. So these are now equally strong. So real estate and PC1, they're strongly correlated, but in the opposite. That means if I increase real estate, PC1 decreases. Right. So you have to do that for the other ones. Again, it's simple. Once you're able to do PC1, PC2 is the same. You just put in the eigenvector. So PC2, remember, is the second largest eigenvalue. Okay. So second largest eigenvalue is 6. So for 6, this is what we got, 1, 2, 2. So we put 1, 2, 2. Again, all of them has positive correlation with each other. So the inputs or the dimensions, they all have positive correlation with the principal component 2. Again, these ones having bigger, stronger correlation. Again, these are ratios. So, you know, a value of 2, 1, 1, it just tells you this is twice as big as this. Okay, so you can normalize them if you need, like in terms of you can make them all to 1. So that means this would be 0.5, this would be 1, this would be 1, for example. So that's the kind of thing you get. Again, here you can have principal component 3 is the same. 1 minus 1 is 0.5. You can see a negative correlation here. These are equally strong, and then this is weaker correlation there. So sometimes you might see 0. So in the eigenvectors, so if you see, let's say there was a 0 here, it means that that principal component does not correlate to this. It doesn't need this in this calculation. There's no correlation between principal component 2 and the real estate, for example. So again, just to highlight, that's a negative moderate because we are comparing it maybe to these values, but it's a negative correlation. So the third one is how many principal components are required to explain at least 70% of the total variance. Provide calculations to support your decision. Again, to get full marks, you have to provide the calculations. You can't just say 2 components or 1 component. You have to provide the calculations in an exam setting for us to be able to say, okay, you didn't guess, right? Because the answer is either 1, 2, or 3. You have 3 components, right? But you have to show us that you actually calculated to come up with that decision. So it's important to show the calculations. So the calculations, we kind of did them. Part of them. So we know that PC1 contributes to 50% because its eigenvalue is 9 divided by the total number of eigenvalues, which is 18, it's 50%. So we know it's 50%. So we know that it's not 1. But then when we add it to PC2, which is 33%, we get to 83%, which is now above the 70%, which means we only need the 2 components. So PC1 and PC2, if I add them, you get 83%. They are above 70%. They explain more than 70% of the variance. So that's the answer. So you need 2 components because of this calculation. Again, you need to show that to get the full marks. The last part, construct a scree plot based on the PCA analysis. Again, this should illustrate the eigenvalues and help visualize which components contribute most to the variance. So I'm going to do this in 2 parts. I know that they ask the scree plot in terms of eigenvalues, but the scree plot can be plotted in terms of explained variance as well. So I'm going to do that first. But again, in the exam, make sure you follow the instructions. Here, they want the eigenvalues, which means that the eigenvalues should be on the y, y-axis. So if you do that here, you have this, and then what you're going to end up with, this graph here, where you have the x-y axis, and you're going to have the explained variance and the principal components. So you're going to have 50%, the 30%, and the 15%, or close to 16%. And then what you're going to do is you're going to have the PC1, PC2, PC3 components there on the x-axis. And then you're just going to put the dots. So for PC1, for PC2, for PC3, and then you're just going to drop. That's the scree plot. Again, that's exactly the same when you have the eigenvalues. So this could be represented as eigenvalues or explain variance, either way. It's just showing the same thing in terms of these are the amount of components you need to explain this amount of variance. So that's the end of the question. See you in the next video.